Do you see the bar? Yeah, okay. I have confirmation from Peanut Gallery. I will begin with a word of prayer. So, dear Father, we thank you for this day again, Lord. Thank you for these students, and we thank you for the weekend, which is about to start. I just pray you'd help us use this time wisely just to draw our thoughts together as we prepare for the first test in here, Lord. In your name I pray. Amen. Okay, so let me just say a word about the part of this I have already solved. So I will post at least this much sometime soon, and hopefully by the end of today I'll have a complete solution, and hopefully my scanner at home will still be working. I'll figure something out. Anyway, I do have a birthday party to attend this evening, so you know, I'll be a little bit delayed, but so mission 3 you guys have been playing with. Let's look at my solutions to the first few problems. Problem 37, what condition is needed for ABC to be in the span of that? So the first way you might solve it is just try to solve the spanning equation, right? Try to find C1 and C2 such that that plus that is ABC. Yeah. Now, so you do row reduction. I mean, you don't really need to get to the reduced row echelon form, but once you get to this, it's even really once I got to that, it was already clear that I needed B minus 2A plus 2C to be 0. Otherwise, that corresponds to an inconsistent equation, right? Which would mean that the original system is row equivalent to an inconsistent system, which would then mean the original spanning equations have no solution. So certainly we need B minus 2A plus 2C equal to 0 for consistency. More than that, if you do have it, you could set C1 equal to A minus C and C2 equal to C to find the explicit linear dependence, right? Although I didn't ask for that. I just asked for the condition on A, B, and C, which is needed for that to be in the span, and that's the condition right there. Now, the other way you could have looked at this is that we know if we have three-dimensional vectors, they form a linearly independent set if and only if the determinant of the corresponding matrix is non-zero, right? So to get linear dependence, which is what we would need for ABC to be in the span of these two guys, linear dependence is accomplished by the determinant of this particular matrix being 0. And this determinant gives you exactly the same condition minus it, in fact. So this is the other way you could have attacked this problem. Now, shoving the vectors in a big old determinant and, you know, seeing as the determinant 0 to detect linear dependence, that's only an option that's only available if the number of vectors considered happens to match the number of dimensions that you're working in. So like here, it won't work, right? Because I've got 1, 2, 3, 6-dimensional vectors, and I'm asking the question, is this other 6-dimensional vector in the span, right? So I can't use determinants in any kind of nice, simple way to solve this problem, right? I need to go back to basics, ask the question, does the spanning equation have a solution that's equivalent to doing this row reduction? Of course, I use technology, as I asked you guys to, or I said you could if you wanted to. I mean, it's like 12 row reductions or something, right? But anyway, it reduces to this, which then says that, hey, wait a minute. So 7 times column 1 minus 1 times column 3 is equal to the 4th column. That's manifest in this. So by the column correspondence property, 7 times that minus this should be equal to that. And indeed it is. You can check it. In other words, V is in the span of S. You notice I called this thing V, and I said that that's S so that I didn't have to write these again. Right? We should try to be precise, right? Saying it is in the span, it sort of works here because there's not a lot of things floating around to be confused about, but it's a bad habit to get into because we will soon have multiple vectors, and when you say it's in the span, the question is which vector, which span, right? So try to get in the habit of being precise in terms of your referring to mathematical objects. It's the best habit to get into. Problem 39, I gave you the reduced row echelon form of A. I told you column 1 was that. I told you column 2 was that. The point of this problem is to notice that in R, we have column 3 is 2 times column 1 plus 4 times column 1. That's just, you can see that just manifest here, right? This is 2 times that plus 4 times that. And this one is 3 times the first minus the second. And the last one, well, that's 0. So I mean, you know the mechanics of row reduction. If this is 0 like that, that means that the original column, that original column must have also been 0, right? If you search your heart and think about row operations, there's no way you can take row operations and change a non-zero column to a completely 0 column through elementary row operations. But anyway, you could also see it as a linear dependence, right? Column 5 equal to 0, that is a stupid linear dependence for column 5. And the column correspondence property says any linear dependence found in the columns of the reduced row echelon form must also be present amongst the columns of A, because A is a row equivalent matrix to the reduced row echelon form of A. So that allows me to build the third, the fourth, and the fifth columns of A from the pivot columns, which are 1 and 2. In particular, I get that, if I didn't make an arithmetic mistake. Does that look like what you guys got? And that's the unique answer, right? Because there's no ambiguity here. I mean, the reduced row echelon form is uniquely determined by its pivot columns, and the column correspondence property preserves this uniqueness to A as well. You could do a proof by contradiction or something if you're not satisfied with that. Suppose there were 2 different A's, right? They would both, well, anyway, you could get into that. Problem 40 is really not that exciting. That's just, hey, were you paying attention when I motivated the determinant? This is not a complicated problem, right? The 1 is 5, the 1 is minus 5. The difference is A counterclockwise rotates to B, that's why it's positive. B clockwise rotates to A, that's why it's negative. The significance of the magnitude is it's the area of the parallelogram. And then to calculate the volume of the parallel pipette, you just put those in a matrix, determinant, whatever that works out to. I got 41. Do you guys get 41? Okay, good. So we're either all wrong or all right. Good sign. Now this one, some of you probably did with row reduction, fine, but we should all agree on the answer. You should have, through row reduction and that kind of logic, come to the conclusion that you needed K naught to be 1 or 2 in order to have linear independence, in order to have a unique solution to C1 times that plus C2 times that plus C3 times that equal to 0. When you look at the augmented coefficient matrix for the linear independence equation, it ought to only give you the 0 solution based on the assumption that K1 and the K is neither 1 nor 2. But of course, we can also use, since we've got 3 three-dimensional vectors, we can shove them in a matrix, take the determinant. This determinant will be 0, will be non-zero if and only if the columns are linearly independent, which of course is equivalent to that matrix being invertible, which is equivalent to another 8 things we could list off, right? But anyway, more to the point, the determinant's 0 if K is 1 or 2. So those we must avoid to avoid the linear dependence amongst the columns. So linearly independent for K not equal to 1 or 2. That's what I got. Problem 43, the determinant of the 3 by 3, whatever method you like. I just expand across the top row because it's just my system. It's not always most efficient, but it's just like hardwired for me at this point. So I just write it down. Right? Right or wrong, that's what I do. You can do something else. I don't know. Whatever. Now this one here, you notice that if you take the second column and the fifth column and you flippity-flop them, then it's an upper triangular matrix. And the determinant of an upper triangular matrix is the product of the diagonals. So I warned you guys in the help session that elementary row operations are sometimes vastly simplifying if you know how to use them with care for calculating the determinant. This is sort of the penultimate example of that. A simple row swap making it diagonal, or upper triangular, lower triangular, then you just multiply the diagonals. You notice the minus is important to notice, though. That has to happen. Do you guys also get minus 5,598,720 for this one? Okay, good, good. Thought it was wrong. No, yeah.
What's the reason for putting the negative in?
I flipped the second and fifth columns. The reason I did that was to make it into an upper triangular matrix, because then I can just multiply the diagonals. Yeah. Down here, notice that A is 3 by 3. That's why I pull out a 2 cubed, because you have to pull out a 2 from each column, essentially. B is 5 by 5, so I have to pull a 3 out from each of those 5 columns using the linearity in each column. Each one pulls out a 3, 3 to the 5th. So I thought I should show you that because I bet you didn't calculate it that way. Am I right? Yeah. I mean, I didn't even give that advice to one of you who came to my office because when you talked to me, it just didn't occur to me at that time. Now, these are not especially exciting. These are really just trying to make you aware of another calculational technique, which I don't really advise you use. I just wanted to play around with it a little bit. So these two vectors are clearly what? These are clearly linearly independent because A is not a scalar multiple of B. For two vectors, we can check linear dependence or independence. If one is a multiple of the other, they're linearly dependent. If not, they're not. You can look at these two and see that B is not a multiple of A, right? Anyway, so when we look at the determinants of the submatrices, one of them 0, but that does not imply linear dependence, right? In fact, if even one of these subdeterminants is non-zero, it implies linear independence of the vectors. So these are actually linearly dependent. How I got that was twice the first one minus the, twice the first one plus the second one gives me the third one. See that? 2a plus b is equal to c. So these are in fact linearly dependent. And that is the source of why all of these subdeterminants are, every one of them is 0. Now, by the way, I didn't even use my top row calculation here. How did I do this? Like, how did I know that this was 0? I just look at this, I go 0. What's my thought process? Do you know? One of our fundamental theorems for determinant, if there's a repeated row, it's 0. So I can just look at this and go, oh, 1, 0, 2, 1, 0, 2, 0. See, because if you can flip the row and you get minus what you started with, what happens if you got the matrix is equal to minus itself? We're working over real numbers, right? So, or rationals or complexes or... Anyway, the point is that that's 0. If it's minus itself, it's 0. So it's easy to see that if we have this property that whenever we flip rows we get a minus, it must be that a repeated row in the matrix gives us a 0 determinant. And the same for here, right? Repeated row, repeated second and third row. So I know those are 0 without further calculation. I didn't even expand into sub. I mean, here I hadn't noticed yet. I was still expanding on the top row, right? Because it's just a knee-jerk reaction. I don't even think sometimes, and I do that. But if I had just taken a microsecond to think about it, rather than just calculate, like you guys do, and I do sometimes right here, right? I could have noticed that that and that are the same, so it's 0. Without further calculation. Repeated row, 0. If I give you a 10 by 10 matrix on the test and I say calculate the determinant, do I probably want you to expand into a sum of 10 9 by 9s weighted with the coefficients of a row or column? No, probably there's some kind of trick to simplify the calculation, right? It's probably a heavy-handed way of me asking, have you learned all of the various tricks of the trade here for calculating determinants? So. Oh, and that's all I got. So, just sorry, sort of anticlimactic. I didn't get to the wedges yet. And that's kind of more of a breadth homework thing. The last part of the homework is more really relevant to the test, right? Like certainly. Especially, like problem 50, 51, 52, 53, 54. These are more test-worthy kind of things. Oh, do you want me to? I can tell you the answer. For this one, what did you guys find? What was the answer to 53? Yeah. Right, scalar multiples of the identity. Those are the matrices which commute with everything else. That's exactly it. And your answer should involve 2 parameters. Yeah. There's infinitely many such polynomials. All right, so I'll shut up. Do you guys have questions? I mean, the test covers everything up to this point, but, determinants, systems, linear independence, and spanning in the concrete sense of column vectors, but yeah.
I don't necessarily have like a specific question, but really
when I make a test, I try to test if you've understood the material covered. So the more mission problems you understand, the safer you are. Yeah.
Is it possible for you to ask us a few proofs that you haven't done in class or
Yeah. Which one?
I guess whatever.
I mean, it varies. There's some sort of just basic common decency. Like, is it very unlikely? Just let me pick on something. I don't want to pick on everything, because if I pick on everything, it's basically just giving you a license not to study the things which aren't on the test, which is sort of exactly opposite to our more general goal in here, which is to educate you. So one thing I will say is, proof of uniqueness for the reduced row echelon form. There's like about a 2-paragraph proof in my notes that proves that the reduced row echelon form is unique. That is something I would be shocked, absolutely shocked, if I put the proof of that on the test, because it's very technical. Well, just also in terms of like misery, the thought of grading that is just horrible to me. So there's that. I mean, you can always kind of bank on my laziness. That sometimes is insightful, but let's see. There are certainly other basic proofs that I have not done in class, but are involving this same proof skill set as things I have done in class. So those are by far more likely. Will there be a proof which involves, I mean, the things you should know, right? Like definition of matrix addition, definition of matrix multiplication, how the definition specializes for column, like matrix column or row matrix, or, we had like 4 kind of special cases I took the time to like try to sort through this semester. Because, yeah, I mean, I can rattle off the matrix multiplication definition, right? Which was what? A, B, right? Ij is the sum over k of ai k b k j. Let's say k equals 1 to p. And here I'm supposing a is m by p and b is p by n, right? I mean, I can write that down, and that makes sense for many cases, but it's also understood that sometimes we delete an index, right? And sometimes the sum collapsed to nothing, we found out. There's a lot of different nuances there, right? But certainly you need to know that. And how to, this is kind of stupid, but this is actually kind of important. If I ask you to prove something about sum of matrices, and you don't have clear in your mind, well, the definition of this is, that, well, it's hard to operate, right? If you don't know that the definition, if when I write this, you think I'm not writing anything, then you have a problem, right? Because on the left-hand side there, I have the ijth component of the matrix C times A, whereas on the did I say right-hand side? I meant left-hand side. On the right-hand side, I have C times the ijth component of A, right? So you should also understand operationally that to communicate to me you understand, if you try to communicate to me that you understand what I just said, and you can't be bothered to write these parentheses here, that communicates a fundamental disrespect for what we're doing, and I will take points off, because I can't tell what you mean. So this becomes an issue in something like, suppose you're supposed to prove, like one of your homeworks this time was something along the lines of C1, what was it, C1, how'd it go? I don't know, A, C1x, right? Plus C2y, I haven't had a chance to write the solution out to that one yet, right? Now, see, maybe you can get away with just putting ij here, Maybe you can get away with that. Maybe that's even logical, but just, to be safe, to make sure that we understand each other, let's just put some parentheses here so we understand we're talking about the ijth component of this whole matrix, right? And then, like, what would my next step be? Next step would be, this is sum, right, over k of A, ik, and then parentheses, kind of important, C C1x plus C2y kj, right? The point is, I'm applying the definition of matrix multiplication to the matrix A times this other matrix. This is playing the role of B in what I just erased, you know? And then over here, I should write something like definition of matrix multiplication, right? You don't have to be super verbose or write complete sentences over there, but enough that I know that you understand what you just did, right? And then what's next? Well, this I can break up, right? That's C1x. And see, the parentheses here are kind of important, because without them, I don't know that you know what you're doing. And classically, this is a problem students have. You guys are super stingy with parentheses. Now, I am the opposite way, too much, admittedly. And then the other thing is, just a warning, like these are equalities because these are matched, right? You write implies here, I will take off points because it shows that you're not really sure what you're doing and you're just hedging your best by putting implies, because at some point you found out that if you put implies when things weren't really equal, you could get away with it. And so it's just kind of a safety buttress for a unknown, but there's some ignorance there, but it has to be masked over. I mean, I understand. I've done the same thing myself at various points in my life. This is addition, right, of matrices. Definition, sorry. I should get like a definition stamp definition. And then what? Then these, what do I do? Right, this is C1 times x kj plus C2 times y kj. You could put dots here if you like, I don't know. Now that is what definition of what? Of scalar multiplication of matrix, right? In fact, I did that 2 times, one for each sum and, right? Finally, now what am I looking at? These are all elements in some ring, so I can pull the C1 out. And of course, I should have had k equals 1 to p, k equals... See, this not writing k equals 1 to p, it's entirely possible I wouldn't take off points for that. Not including parentheses to indicate that you understand the distinction between a matrix and its components, or where the definition is being used, that's much more likely to lose points, as opposed to forgetting to put the range of, you know. Anyway, so this is AIK xkj plus C2 sum over k equals 1 to... I mean, we did a bunch of this kind of stuff in class before, right? Now, admittedly, I kind of skipped a step right there. I hope you don't mind, because I'm run out of board. I mean, we could distribute it in here first, right, and then use properties of finite sums to... So this is... I'll summarize what here is. By arithmetic in the ring, right, and properties of finite sums, and then finally, finally, what do we have? We have C1. This is AX ij plus C2 AY ij, right? And that's what? That's by the definition of matrix multiplication. We're still not done. Next step, that is C times AX, C1, AX ij, plus C2, AY, ij, again by what? Definition of scalar multiplication. Then, what's next? Put them together, right? CAX, C1AX, plus C2, AY, ij, by what? By definition of matrix addition. Aha, I have finally shown that this, the ijth component of, is equal to the ijth component of that. For arbitrary components, it follows then that a times c1x plus c2y is equal to c1ax plus c2ay, which I'm not going to write because I'm tired. But you should write. Yeah. So let's see here. I mean, I think in some sense, I skipped a step going from here to here. But, you skip one step, I probably look the other way on it, right? If you only have 3 steps here, it's probably not going to do it, I need to see that you understand the mechanics here of what's going on. That said, this is not the greatest test question, right? For a couple of reasons. Number one, I talked about it explicitly today, so it's just not my style. I'm just kidding. That's not, you can't bank on that either. See, the larger point is I want to zig when you think I'm going to zag, and so forth and so on. I mean, I want you to study all of the material. It's not a game for you to decide what I'm going to put on the test. The answer should be in your mind. Everything is on the test. You need to understand everything. That's what we want. That said, there are homework problems which are clearly breadth, like the differential one and the wedge one, right? Where do those appear? Those homework problems. Only in those homework problems. That's it. Those are problems that I'm trying to show you things a little bit beyond the course, really, right? So if there's something like that on the test, it would be bonus. It wouldn't be part of the meat and potatoes or whatever, rice, whatever floats your boat, dinner rolls, I don't know. What's your preferred carbohydrate? Rice? Okay. I'm sorry, I think I blathered on about this entirely too long. There are just a few, so we had at the start of the course these kind of mechanical index pushing theorems, right? If you can get your hands on old tests, and I don't know if it really helps you or not, I try to make new ones up every year anyway. But if you could, and you were to look at the first test in here for the past, I don't know, 4 times I've taught it, who knows, maybe more. It'd be hard to find a test where I have not put the proof of the sock shoes theorem on the first test. And if you look back, you'll find it's almost always a homework problem, right? So that's a pretty good one for me to put on there because it's got this kind of calculation, but it's, if you really know what you're doing, you can do it in 3 or 4 lines. But, we had some sort of more interesting theorems that we proved lately about invertible matrices and the relation to like only the 0 solution. So I would try to understand those proofs. Here's another thing I can tell you for certain that's not on the test if you're interested. There's about 3 pages on the chapter in determinants that it gets really, really hairy in there, right? Like where I try to prove, I sketch the proof at least of, the formula for the determinant versus Laplace's expansion by minors. That is obviously not something I would test on because it's just very technical and really not something I've even done in class. So I can't say just carte blanche that just because I haven't done it in class, it wouldn't be on the test. But generically speaking, as a rule, if it's kind of similar in difficulty to something I've done in class and it's related to the same skill set of things I've done in class, it's still very much on the table. Is a shorter answer I should have given you 10 minutes ago. Yep. Oh, how many problems are going to be on the test? Always popular question. The answer is, of course, enough. But too many if you don't understand what's going on. So these are both things that are true. I don't know, it ranges between 10 and 22, something like that. If I ask 22 questions, it's 22 little short questions that you either, know or don't know. It's easy to ask 10 it's easy to ask 10 true-false questions that if you know what's going on, you can answer bam, 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 bam. If you don't, they'll just be like, what?
So do you consider each of the problems on the missions as small questions?
Each of the problems on the missions as small questions. No. No, I don't think so. I mean, they might be smaller to you when you go back and look at them, right? Like, if you go back, let's go back to mission 1. Let's travel back in time. So, you know, as you go back and look at problem 1, it's like, simpler times, right? But, you know, probably it could be that you spent a long time on part B or part C, part B or part D, right? Because there you were learning that you can't add things of different size. Or maybe you were trying to. Maybe you found a way. I don't know. I mean, I can think of a way. I would just add a bunch of zeros everywhere around, then I could add things together, you know? I don't know. But, you know, problem 2, induction, right? I guess that's always something on my list of things to do. I try to put induction somewhere on the test, you know. But it's hard to find a good induction problem. You might notice I invented a notation for problem 4, which made it easier. So I told you guys to write out in a sentence. I actually invented a notation here. I said that M is the matrix of A plus IB. And so with that notation, I was able to sort of point out the pattern, which was that the matrix of A plus IB times the matrix of X plus Y was actually the matrix of A plus IB times X plus IY. That was the pattern we were supposed to see. Perhaps you wrote that in words, but I invented a name for the correspondence that would allow me to communicate what we were seeing more precisely. Likewise, the inverse of the A plus IB matrix is the matrix of 1 over A plus IB. So this matrix map, it preserves multiplication and inversion, was the larger point there. Now, the point of that problem really isn't so much that you memorize those things. The point of that was really just to get you used to matrix calculation and also do something interesting in the process of it, right? In contrast, the problems I was talking about at the start of mission 3 about row reduction and the column correspondence property, it's not just the calculation that matters there. It's the interpretation that you really are supposed to. Those are. I'm trying to build your intuition and make sure you know the column correspondence property backwards and forwards, like so that there's more to. In that sense, there's more to learn there. Like philosophically, the problem that I was just looking at is very different than the problems at the start of mission 3, which I really do intend for you to understand more deeply, I guess. I mean, certainly you should know that if we take a matrix times the standard basis vector, what happens? If we take A times EJ, what do we get? A times EJ is column J of A, right? EJ transpose times A is what? Row J of A, right? These two facts, at least, we should know. But you should also be prepared to work out things like what is A times E1, 2 or something. You know, you should know what the E1, the EIJs are and what the little e's are. These are standard notations that we're supposed to know going forward. You guys know what transpose means, right? What's a symmetric matrix? A is equal to A transpose. What's antisymmetric? Yeah, A is equal to minus. A transpose is equal to minus A, right? Yeah, that problem is bananas. The larger point there, is that you should. I mean, one of the things I hope you have noticed in the process of doing that problem is you can't just commute the letters around, right? Matrices don't generally commute. We have to maintain order. Left and right multiplications are different. All right, most of you guys can do a problem like this on the test if you're careful. Problem 8. that is all right, isn't it? Like, you're like, you should be like, Dr. Cook, I'm very confused by problem 8. I sure hope you don't put that on the test. Because I would just be totally lost if you were to put that on the test. I mean, that would be a wise course of reverse psychology. Except now that I've said it, it won't work. Right? So then the question is, does that make this problem more or less likely to be on the test? I just don't know. I don't know where we are in this Sicilian debate. Let's see here. It's conceivable that the problem be on the test. It's conceivable. You know, this is a hard problem for me to grade, honestly, on the test because there's so many different ways to attack it, and many of them look like you're not saying anything. But this certainly we should know, and it'd be good if you could prove it, obviously. But the column-by-column multiplication rule is, if you think about it, how many times have we used the column-by-column multiplication rule? It's been at the center of so many different arguments that we've done in the last about 2 weeks, right? I mean, like, so many things. The inverse calculating algorithm, right? How elementary matrices work. We always using this column-by-column rule. Look, there it is, sock shoes. So again, the parentheses. All right, last time I assigned this question on the exam, so many people are like, AB transpose IJ. It's like, well, what do you, I mean, they're just missing, they're missing parentheses, or they'll have like, oh, here's a very popular, like, totally nonsensical thing to write. This is my other favorite thing, is like, you guys, not you guys, but, you know, stereotyping. It's what we do in math, you know. So like, typical lost student move. No IJ over here. No IJ, just AB transpose. And then all this over here, I got like ABJI. Of course, this lost student would not put parentheses. Forget about the parentheses, they're nowhere. And then we'll get like this. And then, or I'll see things like no sum, and it's just like this is equal to that without the sum. I mean, there's so many different wrong things I see. I don't even know where to start. This is not complicated. Spend some time to understand the index notation, please. Or don't. Or don't, it's your prerogative. Augmented coefficient matrices are your happy place. I don't really have much to say about those. You need to know how to interpret them, right? Solution set is a solution set, right? If I just say find the solution, you could either give me a set or a solution, or parameterization of an arbitrary solution. It's up to you. But a set is a set. You know, for a given row reduction, if you start thinking about it, we can interpret it in many different ways, right? Like this row reduction going from here to here. Yeah, I could look at it as 4 equations and 1, 2, 3, 4, 5 unknowns, right? Or I could also look at it as like there's an imaginary row, there's an extra row of zeros here, and I could look at that as telling me something about, you know, a set of 4 equations and 6 unknowns, a homogeneous system. I could also solve that corresponding problem. I could think of these last 2 problems, I could think about this being like a super augmented matrix, and I could think about it as, you know, 2 systems of 4 equations and 4 unknowns. I could do that as well. I would have the solution to both of those using these last 2 columns. I mean, these are all ideas we've explored, right? There are a lot of different ways to look at a given reduction. I don't know if this, somewhere there's an error in the, I don't think it's that one. Anyway, you guys have any questions in particular? I don't. I almost always ask you to find the inverse of a matrix on the test. I mean, that's almost always there. That's a pretty good, you know, if I ask you to calculate the inverse of a 3 by 3 matrix and you can do it via row reductions, pretty good evidence to me that you've settled the row reduction problem. You know what you're doing, you know. And also the inverse matrix row reduction is nice in that you can check your answer. Right? There's a standard way to check your answer. Let's see here. So the grader, I think, told me that he told me something was wrong. I don't have that stupid. I don't have his correction right in front of me. Do anybody know? Anybody looked at this to know what's wrong in the solution? I think he said problem 1. I maybe either copied the augmented coefficient matrix down wrong or something. There is an error somewhere in here of a, hopefully just not of a conceptual sort. Yes. Hey, look back at this problem 22. Do you know a better way to do it now? We're asking what? To solve that system, right? So that's basically, is the matrix, the coefficient matrix here is what? 1k, k4. So the inverse exists only if what? The determinant's non-zero. What's the determinant of this matrix? 4 minus k squared. So k equals to plus or minus 2 are the ones for which the inverse doesn't exist, and there's no solution. Otherwise, there is. So, getting back to your question, are homework questions long? At the start, yes, but when we come back to them, sometimes not. So don't forget, sometimes a 2-hour homework problem in the light of the next chapter becomes something much shorter. Be aware of this. Like, sometimes hindsight is better than 20/20 in this course. This is a good example of that. Of course, if we really had embraced the multiplication by inverse here, this is an easier problem if we look at it from that lens also. I think row reduction actually makes it tougher. Don't forget about your elementary matrices. They don't have to be hard. But if you don't know what they are, they're really, really complicated. They're less than elementary if you don't know what they are, right? Make sure you know the list of equivalent statements for an inverse versus a non-invertible matrix, right? If you haven't watched the help session yet, I would encourage you to. There I talk about something called an eigenvector, which should have helped you with the problem in here, which was about an eigenvector essentially in disguise. We'll get back to eigenvectors later, but anyway. Well, I'll shut up. I'll see you guys Monday. And I should have the rest of the solution up sometime pretty soon. Would it be helpful to you guys? Do you care if I post this right now, or can you wait till later? Wait. Okay. Thank you. Oh, yes.